welcome to the SN1. If you've been following my directions, hopefully you have all of this written out. So I made some modifications from the slideshow. We've got our mechanism outlined, our steps outlined in steps 1 and 2. So we want to break the carbon leaving group and then break the carbon nucleophile bond, or form the carbon nucleophile bond. The overall reaction is shown here. I just wanted to give you that context to set it up. So again, you should have watched the SN2 overview already, and you should already have predicted 90% of what I'm about to drop down on this. Okay. That said, we're going to use the power of pause here in just a second, and I'm going to draw in a bunch of kind of review information. So, power of pause. Here are all our definitions of the pieces that we've got within this. Our substrate will act as the electrophile. Our leaving group will take electrons from the substrate. The nucleophile will donate the electrons to the substrate, but because this is SN1, after our leaving group has left, and then the solvent is going to dissolve or homogenize this entire process. So with that, let's go ahead and erase all of that content and now kind of start swinging away at our mechanism. Because we've established that this is going to happen in 2 steps, we need to address those 2 steps. Step 1, break the carbon leaving group. So that bond needs to break the connection between the carbon and the leaving group. Those electrons are going to need to go with the leaving group because the leaving group is more electronegative. The resulting structure is that we will be left with our substrate and then our leaving group with that extra pair of electrons. Since the leaving group started neutral and now has an extra pair of electrons, we should be drawing it as a negative charge. What happened to the substrate? Well, the substrate just lost electrons, so it should be positively charged. For those of you that have remembered your ion stabilities, this would be a good moment to freak out. We'll worry about that later. We've now completed step 1 of our mechanism. Okay. In step 2, what has to go through and happen? Well, in step 2, we need to then form the carbon nucleophile bond. So our nucleophile with the lone pair electrons are now going to share with that positive charge. Okay. The result of that is now that we have our substrate, we will now have a new bond connecting the nucleophile to our substrate. Okay. This last kind of sequence can be a little bit odd. It typically happens for an SN1, so we're going to show it, even though this technically isn't an SN1 step. The nucleophile started neutral in this case, and it shared electrons, which means the nucleophile is now positively charged. That positive nucleophile isn't so happy, so what does it do? It steals electrons from the easiest place it can get them from, that hydrogen, to go through and form our final product. Okay. In that case, something had to come along and remove that hydrogen. That hydrogen is coming off as H+, which means it's acting as an acid, which means a base is most likely to be present in solution. So the base would need to remove that. That last step is kind of a secondary aspect of our reaction. It's an acid-base step. Okay, we'll talk about that in a little bit more detail later. Don't stress a whole lot yet. Okay, so at first we have our heterolysis as step 1 of our SN1 mechanism. And then we also have the coordination as step 2 of our SN1 mechanism. So now let's think about and address our results. Okay, we're really only going to focus in at the heterolysis and coordination. We have 2 steps. We need to be focused in on which of those 2 steps is going to be our slow step, because that slow step is going to identify the important step that addresses all of the basics of our overall reaction. So if we go through and look at this, that first step, we're starting with something that is neutral and going to charge, and then we're going from a charged structure with a missing octet, okay, to a charged structure with an octet. So if we were to consider this on an energy diagram, which we didn't need to do for the SN2, in an energy diagram, we're starting probably neutral, we're going up in energy to form an intermediate, and then we're going back down in energy, which means our rate limiting step is probably that first one where we're going from neutral to charged. Okay, why does that become important? Well, my rate will now be equal to my rate constant for this reaction, and it's only going to be concerned about step one, the heterolysis. The coordination is going to happen incredibly fast, so I can effectively ignore it. And really all I need to worry about is that heterolysis step. What reagents are involved in the heterolysis mechanism? Well, in that step, the reactant, there's only one. It's the substrate. Okay? So this is going to change the process of how I interpret this reaction, because it's now a different mechanism. There's a bunch of stuff that's happening, but there's only really one part that is the crux of this argument. Okay? And that's why we need to address that slow step and focus and find it. And this is why energy diagrams become important. So when we go through and do that, our focus is now really just going to be centered on what is happening in that first step. Okay, just the heterolysis. So I'm actually going to do a dotted line through our mechanism over there, because I don't really care about the nucleophile attacking. Okay, cool. So how many species are involved in my rate limiting step? Well, there's only one thing there. This would be a first order reaction, also known as unimolecular. What does that mean for me? I could now write out the name of my reaction as an SN1, where the 1 is referencing the order of my reaction. I could also write out the full name as a substitution involving a nucleophile, so substitution nucleophile, and it is now unimolecular because there's one thing in the rate law. That's where the name comes from. Not the number of steps, but the rate law. Okay, so cool. We now have a context of where that information is coming from and why it's potentially relevant. How does this now then apply to the rest of our reaction? Okay, well, let's piecewise through this. We've got those 4 components, so let's start with, let's actually start with the nucleophile. Okay, why start with the nucleophile? Is it in the rate law? No. So is the nucleophile important to me? No. So when it comes to the nucleophile, it is kind of irrelevant. And before you start going, oh, well, I don't have to worry about the you need a nucleophile. It's still a nucleophilic substitution reaction, okay? But it's just not involved in the rate law. So its presence is important, but I don't care about its concentration or its activity. So what does that mean? The nucleophile does not need to be strong. Okay? And so this allows me to differentiate, because if I can identify what nucleophile I have present, if it is a negatively charged nucleophile, that suggests SN2. If it's not negative, i.e. it's weak, that suggests SN1. Okay? That information directly falls out of interpreting the mechanism as we've just done. So that's kind of neat. Okay? So after that, leaving group, as we kind of addressed already in the first one, we need a leaving group. Okay? So the leaving group needs to be good. Okay? It's usually good. Arguably in the SN1, it needs to be better than it is for the SN2, because if the leaving group isn't good, it never leaves on its own. Okay? And that's what has to happen in step 1. Okay? That better than SN1 or than SN2 mechanism is pretty weak and it isn't easy to distinguish and identify. So I wouldn't stress about that. Again, leaving group as an important thing isn't really a big deal. Okay? But the substrate's going to be a big deal. And as we addressed with the SN2, the classifications we need to be coming up with are primary, secondary, and tertiary. let's take a look at the mechanism that we've got drawn. What substrate did we draw out? Okay. Well, I only see one carbon connected, which means there are implied 2 hydrogens to that carbocation. A primary carbocation, as you may remember, is incredibly unstable. Okay, or rather not the most stable. To make it more stable, what I would need would be carbons connected to it, a tertiary. Okay, so I could look at that substrate, and if I identify that that substrate was a tertiary substrate, it is going to do this heterolysis step very, very fast. Well, if the heterolysis happens faster, the SN1 reaction is more likely to occur. Okay, so a tertiary substrate reacts faster than a primary, or faster than a secondary, faster than a primary. Okay, and that's really driven by the stability of the carbocation. So while most students will go through and memorize this tertiary, secondary, primary, I would argue the more important aspect is the stability of the carbocation. And why? Is there something else that contributes to the stability of a carbocation beyond substitution? Yes. And if we look at stabilities for any charged species, the substitution is the last thing to be looking at. We should be evaluating the atom and molecule effects, i.e. resonance. So resonance will play a really big deal when we're looking at our SN1 mechanisms, because if there's resonance, that can stabilize that carbocation, and that's really going to drive the speed of the SN1 reaction faster. Okay? So be aware of that. Remember that when dealing with your SN1s. Okay? So it's really all about that carbocation. After that, we've got our solvent. Okay, well, what solvent should we pick? Now that I've written everywhere and have no space, I'm going to erase that slide 44 number at the bottom. So in our solvent, okay, again, we had those 3 characteristics, and I'm not going to write them. Well, I can write them out. We have our protic, we have our polar aprotic, and we have our nonpolar. Again, look at that slow step. What do we have? Okay, we only have one reagent. We have this fairly nonpolar, and I should be writing that in green because we're addressing kind of solvent aspects. A fairly nonpolar species. It's got a little bit of polarity with that leaving group. Okay, so we might call it partially polar. Polar question mark. Okay, so we might go, well, I want a nonpolar solvent. Okay, that's fine. That nonpolar solvent is going to dissolve that starting material. I don't have that ionic nucleophile to stabilize, so maybe a nonpolar solvent would work. Okay, but we do have to evaluate what's happening in that first step. It's not just that I have these things present. I also have to be able to form the products of that first step. Well, if we take a look at those products, those are exceptionally polar. We're getting a carbocation and an anion in our leaving group. Those exceptionally polar substances would not be stabilized by a nonpolar solvent, which means the instant they formed, they would reform, and we would drive this reaction back towards our starting material. That becomes exceptionally problematic. So I don't want that to happen. So a nonpolar substance is not a good idea. Okay? So we have our polar aprotic and our protic. Okay? Well, both of those are polar. They could go through to stabilize the ions. When we looked at the SN2, we said no to the protic because I needed to dissolve the nonpolar compound. Okay? I don't really necessarily need to dissolve the nonpolar compound. I need to be able to dissolve the intermediate. I need to be able to make those products. If those products in my step 1 don't form, the reaction doesn't occur. I don't care how fast the subsequent steps happen. If that first step doesn't happen, the reaction doesn't happen. So what do I want to do? Well, I want to make those species as stable as humanly possible. Okay? Which solvent is going to be the best to stabilize a positive and a negative? Okay? The protic solvent is going to generate the largest partial charges. Those large partial charges will do the best to stabilize the positive and the negative, which means when we're moving to an SN1, the best choice for a solvent is actually a protic solvent because it will stabilize the intermediates. This is a little bit different than our SN2. Our SN2 was we have 3 choices, 2 of them are awful, we take the best of the remaining pieces. In the SN1, we're actually picking a solvent because the solvent helps the mechanism. It's not the best of our options. It literally helps the reaction happen. So our solvent choice becomes a lot more important in our SN1, and that's why we end up picking that solvent as our choice, our protic solvents. Okay, so ideally what you now have is 2 sets of notes, one looking at SN2, one looking at SN1 with all of these little bits and pieces and summaries associated with them. You should be able to start now making comparisons between these to decide what things would allow you to trigger to do one mechanism versus another. Okay, and we're going to go to that slide in just a second. What I'm going to do is clear all of this away so we can actually see the prettiness, sort of prettiness of everything underneath. And this would be kind of our big summary for our SN1. One of the things that's missing on our SN1 is that we need to be able to say carbocation. Okay, so when I say SN1, you should be saying carbocation. So carbocation drives all of your decisions. When I say SN2, you should be saying backside attack, because the backside attack is what drives virtually all of your analyses. Okay? And then the last thing that I was alluding to that you should be considering is when you're comparing these 2 reactions, you should be comparing them, this is going to suck, sorry. You should be comparing them in context of this table. So we've addressed the nucleophile, leaving group, substrate, solvent. You should be now starting to go through and be like, well, what do I want for this? And start to fill this table in. For an SN1, no, I want a weak nucleophile. For an SN2, yeah, I want a strong nucleophile. Okay? For the leaving group, it should be really good for the SN1. It should be good for the SN2. Okay? For substrate, I preferred tertiary over secondary over primary. Okay, for the SN2, it was the other way around. Primary over secondary over tertiary. Kind of get the idea? So as we discuss each of these mechanistic options, you should start to fill these tables in so that when we get to the point in chapter 9 where you have to look at a reaction and classify each of these pieces, you'll now be a step ahead and be able to say, well, based off of that information, I know I'm doing SN1 or I know I'm doing SN2. Okay, so with that, this video is already way longer than I wanted it to be, so I'm going to go ahead and stop. I think we've got a decent foothold on where we should be going from here, though.